Hello physics seers, this is problem 10-1. Okay, let's get started. Let me just set all this stuff up. Alright, part A says that we need to find the direction of the field that is necessary in order to contain the charge that is flying through region 2. Okay, so if we can look this like with the perspective, just get a better sense of what's happening, we can see two plates, one here and one there, with the charge flying between them. There is the magnetic force is going in this direction out of the page. So we need to find the direction of the electric field in order to contain this movement. So by using right hand rule shows us that since the charge is moving in that direction and the magnetic field is going this way, the force must go down. So the force on the charge from the electric field must be going the opposite direction. So on a positive charge, the electric field must be going up in order to oppose this force that is caused by the magnetic field. Okay. Part B asks for the speed of the charged particle. This is the same thing as before, except we're actually using an equation now. So the equation is for the force on a moving particle through a magnetic field. It's the charge of the particle, its speed, dot B, and the charge on an from an electric field is E times Q. The Q's cancel out, so all we're left with is VB, because it is perpendicular to the velocity is perpendicular to the magnetic field, is equal to E. So V is equal to E over B. Part C asks for the mass of the charged particles. And if you look at the problem closely, you will see that in this region, right over here, if the mass is greater, the radius of the circle will be greater as well. So you can assume that you can use potential energies or the forces to determine the mass of the charge. And the forces that we'll be using here is centrifugal acceleration and the force caused by the magnetic field in region 3 and the velocity of the particle. So for part C, we can use the centrifugal acceleration, mass, the mass of the particle, which we will be finding out, times the velocity of the particle, which we have over here. So mass times V squared over R, which is the radial acceleration, centrifugal acceleration, times the force caused by the magnetic field, which is just QV dot B. The V over here cancels out, so we're left with M is equal to QB over V, and the R comes to the top. So when we plug in V over here, we can plug that for V over there. So we get M is equal to Q, B, the B switches places since it's underneath, since it's the denominator, R over E. And that is the mass of our particle. Now we can move on to part D. It's a tad trickier. It asks for the accelerating potential V in the region I. So the potential, the energy potential from region I is equal to the voltage potential change times the charge of the particle. And the after region 1, the total energy is conserved throughout the whole experiment. So QV, which is the potential change in the region, is equal to the ending potential energy, which would be 1/2 mv squared. And we can use the V from before. So we now have QV is 1/2 the M value, which is times the V value squared, which is, so we bring out the terms. Cancel. And now we can find the V value by just simplifying the terms. Well, it seems that they've been using big R. Let me just put over here that R is equal to small r, just for my sake. And now we can go to problem E, or part E, which asks for the acceleration A of the particles for region 3. So the only acceleration happening in that region is the centrifugal acceleration we were talking about before. So all you really have to do is use the centrifugal acceleration in V squared over R. So the centrifugal acceleration is equal to V squared, which is over R. Hi Zodi. My dog just came into the room. So we can cancel out now, or I'll use the big R. So we end up with like so. So we got the velocity, the EV, and it just goes to that. Now part F. We're on the home stretch. The time required to move along the semicircular path in region 3. So all we have to do is find the length of that path, which is 2 pi r over 2, since it's only a semicircle. So pi r is the length of the path. I keep on using these small r's. R. So we get pi r is equal to t, the time it takes, times the velocity it uses while taking the path. So we get pi r is equal to t times the velocity, which we got at the beginning, which was e over v. And then we just bring it the terms. Pi r v over e is the time it takes. And that is problem 10-1. We can look at all the sheets now. Make that E more clear.